All right, so we talked about regression, and the next category of supervised learning problems is classification. This is where we do not have a continuous value for the output. It's basically a label that we have. So for example, in the case shown here, the label could be blue or red. Is the new sample blue or red? Or the label could be square or circle, right? Or something else. But it's a binary classification problem in the case shown here. What we want to figure out is that based on those two features that we have, x1 and x2, does a new sample belong to class circle or to class square, right? So how do we figure out how do we classify a new sample? So the goal is that, for example, y identifies class 1 and 0, or something belonging to class. If y is 1, it's true, it's, let's say, yes. It means that if y is 1 for a set of features, it means that that sample, that particular sample, belongs to class that we are talking about. And if it is 0, it means it doesn't. It's a 0-1 question, binary classification. And the goal is to come up with a function that once you give it that set of x values, the features, it can come up with a value for y. It can predict the class for you. And obviously it's a nonlinear function. Right away you see this is a nonlinear exercise. The output is either 0 or 1. The input values, the features can change actually a little bit, and the output may not change, or a small change in one of them can switch the output from 0 to 1, and then maybe the small changes over there. So let's say if once you are put in this class of circles, small changes in x1 and x2 do not make a difference at the output. Or once you are here, small changes in x1 and x2 do not make a huge difference. You stay in that class. So it's a nonlinear problem. Only two outputs, 0 or 1, yes or no. And we are going to start with this binary classification problem. Obviously, you can have multiple classes, and we covered them later on. For now, we're going to focus on a binary classification situation. So what is the goal? What we want to do is that maybe come up with a continuous function, f, right, that has some weights w, that you go and apply these weights to the features and pass them through the function f and calculate the value for that function. You come up with a threshold. You say if the function value is larger than this threshold, then I'm going to assume that the sample belongs to the class, or output is 1. If it is below the threshold, we go and say it doesn't. So what we need to do is we need to come up with a couple of things. First of all, what is that threshold? Where do I draw the line? Where do I separate these two classes from each other? That is usually the algorithm you're talking about plus the f. And then the second thing is that how do I minimize the error? How do I do a good job in classification? And that's where you go and choose the w's based on the previous data and outputs that you have. So we have seen something like this before. Linear regression was this. You were trying to fit the best you can to this data. Classification actually looks for a line like that, a line that best separates the two sets of the data. And with linear regression, we saw that you basically have one line. Depending on how many data points you have at the input, you get a feature vector w that best describes your data. With classification, you can already see that if I tilt this line a little bit downwards, it's still perfectly separating these two classes from each other. Same thing if I tilt it a little bit upwards. Same thing if I move it a little bit up or down in this space. So you really do not have one option. You have multiple options for the line that separates the two classes in this case. And part of the question is that, okay, so which one of these lines I choose? Another question may be, do I want to choose a line or maybe a curve? Some sort of a high order function may be a better separator here. All of those become problems that we have to deal with. Now, here in this case, that let's assume a line separates the two classes for us, the life is easy. So if all of the members of one class lie above the line and then the opposite class or the other class lie below the line, what I can do is that I can use the function for that line as that threshold, right? So the threshold could be 0. The function for that line will be the basically separator between the two classes. So if a point lies on this line and I calculate that function and then separate, subtract that point from this equation of line, I get 0. So basically 0 separates the two sides from each other, right? So if I put the coordinates of a new data point and it is lying on the line into my equation, I get 0. But I can see that anything above this line will have a positive value. So I can say that 0 is the separator, anything above, anything that is larger than that 0 is part of class 1, anything less than 0 is part of class 2 or class 0. Often, however, we prefer to have a probability. I don't want to know, well, I do eventually. I want to know whether this data point belongs to this class or that class. So 0, 1 is a decision that I'd like to make in the end. But often a probability is more helpful than a 0, 1 output. For example, if your data point lies really close to the line that separates the two classes from each other, well, there is a chance that that data point may be wrongly classified, right? So I would like my algorithm to tell me that I give this data point to have, let's say, a 40% chance of being in this class. It's less than 50, so I would probably go and make a decision later that, it's less than 50%, I put it in this class, I put it in class 0. But at the same time, I know that, this is probably a bit too close to the border. So if I have other indications somewhere else, I may be able to maybe go and revisit that data point, or just, keep in mind that this could belong to the class wrongly. However, if I'm far away from this line, let's say somewhere around here, and I go and do the classification here, well, that data point, that particular data point is deep inside that class. I probably have a, let's say, probability of 90% or more for correctly classifying in that class. Same thing for example, this data point, right? So, or this data point. They are deep inside those, their own internal classes. And I would probably get, I want to find a function that gives me a high probability of correct classification for those that are deep inside the classes that they represent or they come from. And I want to know the marginal cases, the ones that I'm not too sure about. And you will see that this way of having a continuous, let's say, value for classification is helpful later on. We'll see it very soon in a couple of slides that this is actually more helpful than 0, 1. So just take it from me that I'd prefer, in most cases, to have a function that gives me something. It's not really a probability, but something that resembles a probability. So basically, if this data point belongs to that class, there's really no discussion of probability, right? But what I want is to have a function that tells me that, yeah, this guy is deep inside this class, so, I'll make up a number that looks like a probability. I tell you it is 99%. And if you look at this and you want to try to see if this belongs to this class or not, I'll go and try to produce a number, again, in terms of a probability that is close to 0. I say, there's a 1% chance that that belongs to this class. So I'll give you a probability. I'll give you an indication of how far your data points are from that threshold, from the border that you have put between the two classes. So how do I do that? Well, we saw that for data points that fall on this line, I get a 0 value. If I go above this And as I get farther and farther from this line, I get values that are larger and larger and larger, positive. And if I go below the line, I get negative values. So I basically can go from negative infinity to plus infinity. I'm looking for a function that maps all of that into my probability range, 0 to 1, right? So I want to go and say, okay, I calculate the distance, from this line that separates the two classes from each other. If it is very, very large, if it is deep inside this class, I want a probability of 1. If it is very, very small, it means large negative. I want to have a probability of 0 or something that looks like a probability of 0. And there are multiple ways of doing that. One potential function is shown here. So this is called the Sigmoid function. It is 1 over 1 plus e to the minus z. And z basically can vary from minus infinity to infinity. You can see what happens. If z is a very large negative number, then e to the minus z will be e to the a very large positive number, so basically a very, very large number, and 1 over that will be 0. So this is where you will end up being. On the other hand, if z is a very large positive number, going up here, then e to the minus z approaches 0 quickly, and then 1 over that will start to approach number 1. Never exceeding 1, never going below 0. It basically maps the entire range of real numbers to the range of 0 to 1. It approaches 1 very, very quickly. So basically, if you calculate g of, I think around 4.4, you will be already 0.99. So g of 4 is more than 90%, right? So now logistic regression takes advantage of that. So in a logistic regression, the function that we chose is g, the sigmoid of these weights times features. Okay, so this is, if I want to expand it, this is how it looks like. This is the function that I'm going to assume describes the relationship between the feature vector x and the output y. So this is the function, logistic regression, closed form function, relatively easy to understand. As you can see, this looks very much like linear regression that we had before, but I'm passing that function through the Sigmoid function. And what we say is that, okay, so I'm going to put my threshold at 50%. Going back here, you can see that at a z of 0, I get 50%. So that's where my line is. Anything above that line is going to give me a probability of more than 50%. Anything below that is going to give me less than 50%. So once I figured that out, you can see that the WTK, the sum of weighted features, if that's larger than 0, I'm on the positive side of that Sigmoid function. I get a probability that is, or a value that is larger than 0.5. I think about it as a probability, but it's not really a probability. So I get a number that is larger than 0.5, and I say, okay, so if it is larger than 0.5, I think about it as a probability of having a higher probability than 50% for the data point to belong to that class, and identify it as a member of that class. Or if WTX is less than 0, basically I'm falling below that line that separates the two classes from each other, then I can see that f of xk is going to be less than 0.5. Or if I think about it as a probability, the probability is less than 50% for this data point to belong to this class. So I therefore say it doesn't belong to that class. It belongs to, it doesn't belong to that class. Let's just keep it as that. Then I go and define a cost function as shown here. And then this cost function, remember, y is either 0, yk, the predicted value is either 0 or 1. So you either calculate this value or this value. If y is 0, then this first term is 0. If y is 1, then this term is 0. And then you go and calculate the cost function, the goal is to minimize the cost function and figure out what those W's are. And usually we do this through some numerical minimization of the cost function. And that's it. Basically, you figure out what W's best separate the two classes from each other. Now the next question is, what if you have more than two classes, right? So let's say we had this example earlier that you have a picture of a digit and you want to know whether it is anywhere from 0 to 9. So there are 10 classes here. So what if you want to do it what do you do that way? How do you apply logistic regression to that kind of a problem? And what we do here is that we go and say 1 versus all. So let's say we go and train an algorithm to say if this digit is 0 or not. And that's your first algorithm. The second algorithm will tell you if this digit is 1 or not. The third one will tell you if it is a 2 or not, and so on and so forth. And basically you do a 1 versus all kind of classification in each case. And here is why you can actually very quickly see why I would prefer a probability output. Because once you have this digit, let's say it's a badly written digit, it's a poorly written 1 that, let's say, or 3, right? And 3 may be harder to classify. So let's say you compare it against 0, you get a probability of 20%. Well, it's not a 0. You compare it against, let's say, 1s, and you get a probability of 15%. So it's not a 1. You compare it against 2s, 20%. It's not a 2. You compare it against 3s, and well, it's a poorly written 3. It's somebody with bad handwriting, or they missed a portion of the digit. And even against the 3s, when you compare it to 3s, let's say it gets you a 45%. So even that doesn't go above the threshold. So you don't classify it as a 3. When you say 3 versus all, you get 45%. So you don't even classify it as a 3. You say, it doesn't belong to class 3. So 0, 0, 0. And if you go through the entire range of digits, you get zeros for all of them. Well, all of a sudden you have a digit that doesn't belong to any class if you only look at the outputs at 0 and 1. However, if you go and look at the probabilities for this digit belonging to one of those two classes, in most cases you have a class that stands out. So you have a class that, let's say in this case, you had a 45% for this thing to be a 3 versus, let's say, 20% for being a 2 and 15% for being a 1 and so on and so forth. So once you look at the probability of this correct characterization or classification, in most cases you can actually, even among multiple classes, you go and find one that is most likely to be the right class. And then you can identify this unknown object, new data point to that class, or assign it to that class. So in a case like that, actually having a probability-like notation for the output of that function, the classification function, is very helpful. At the end of the story, the user will see this as a class 3. They may not even see that this had this much probability for being classified as class 3. But for you, for the calculations to get to that point, it's better to have something other than a 0 and 1. It's better to have a little bit of legroom to go and change your mind if you need to later on, or maybe go and figure out this is not a lot of confidence that I have in this classification, so maybe I want to test one more thing, or something like that, right? Or at least let the user know. I think it's a 3, but it may not be. Anyway, so pros and cons for logistic regression. It's a fairly simple algorithm, and there are not too many parameters to play with. So therefore, it has, in most cases, a low chance of overfitting to your training data. The probabilities that I have at the output, or the probability-like numbers that I have at the output, are actually very helpful in decision making, and then You can actually go and use it for making a decision. Sometimes, let's say it's a critical application and you don't want to have a 50% threshold for, let's say, assigning something to a class. So let's say you want to put, you want to have a little bit higher confidence. So you can move that threshold up to 70%. You know, if you want to be a bit more sure that this is the right classification, you move the threshold up. That's very easy. You know, it's just at the end of the story, you get that probability-like number at the output of regression classification. When you want to set the threshold for accepting or assigning it to a class or not, it's up to you. And that's very easy to manipulate. And it doesn't actually have any assumptions on the distribution of the data and its properties. It's fairly generic. We see that some algorithms are not like that. The problem is that it can have high bias, right? So because it's such a simple algorithm, you know, it may not be able to take into account all the complexities that there are in your data set. And your options are a bit limited in terms of how you can improve it. You can come up with new features, you can calculate new features, but at the end of the story, it's a relatively simple algorithm. And it may not really deal with categorical variables at the input that well, right? So this is, for example, for the, I don't know if this is a picture of a cat or not. Maybe the color of the skin is a parameter, right? Or the color of the hair is a parameter. And you have categories at the input. And then regression algorithm, sorry, logistic regression does not deal with those kinds of inputs that are there in them, let's say themselves are class labels. Now, logistic regression is simple to implement, is easy to understand, but one of the reasons that it's such an important function to understand or algorithm to understand is that it is the basis for neural networks. So this is a term that you've seen or heard a lot about. I'm going to talk about it very, very briefly here. I'm not going to get into the neural network discussion. But a neural network essentially is trying to mimic what a brain does, a human brain or animal brain does. And then if you look closely, you'll see that each, let's say, cell in your nervous system is receiving input from different sources. Computations are super simple in this case in each cell, and they send out signals out to following cells. But each one of these is simple, it's doing a little bit of work, it's doing a little bit of computation, but there is a whole lot of them that are working in parallel. And the massive computation power of the brain comes from this parallel processing of the data. So for that reason, people have been trying to mimic that using computations and functions. Neural networks, I'll show you the example on the next slide, are among the most powerful machine learning algorithms. There is a variety of neural networks that people can use for different applications. Very, very powerful, very, very flexible. And there's actually a universal approximation theorem that says if you make a neural network with just one hidden layer and a finite number of neurons, you can approximate any function. You can approximate any continuous function using a neural network. So this is actually very powerful, and it's math, right? So this, it must be true. However, the downfall is that, there are some challenges here. What is the right number of neurons? What is the right number of complexity? How much complexity do you need at the end of the implementation when you want to make it? There was, and there has been, and there is still some, a lot of effort on trying to build models of physical systems using a neural network. They call it a black box model, right? So there's a model in this box that is trying to mimic what the function that related the input to the output was, according to the universal approximation theorem. I just increase the complexity of neural network as much as necessary, and I should be able to approximate any function. And people have been trying to do that. It just looked like it's a hammer that actually can go and, basically put every nail through and every board. But it turns out that it's not that simple. At the end of the story, We'll see the problems in a second. Now, one of the biggest challenges with neural networks is that it's hard to figure out how they're doing their job. Right? So they do their job, and we have a theorem that it says that they're basically super powerful. They can take care of many, many jobs. But we cannot figure out how they're doing their job in most cases. And that's dangerous. In engineering applications, that is basically very alarming. You have to be super careful when you're using these kinds of algorithms, because you're basically relying too much on the algorithm. And there could be something that has gone, you didn't set something right, or you chose a function that is too complex and you're overfitting to your data, or you're missing some information in your model. And the neural network can just go and try to fit to your data beautifully. And all of a sudden in the field, it just goes and misbehaves. And it's really hard to figure out what happened. Even when you're doing the training and validation, there could be situations where your validation error is still high, but you really cannot figure out how to reduce it. It's a bit vague compared to some of the other algorithms. And then whenever I do not have a proper understanding of how my system works, I will be very, very careful if I want to use it. Now, here is the structure of a neural network. Essentially, you go and take your input feature. This is from your input layer. We call it input layer. This is where your features come in. You have a hidden layer and output layer. In each hidden layer, you take the features from the input and you perform your logistic regression function on them, right? So your Sigmoid function that you add up all those weighted features and you produce a single output. Then this output is sent to the output layer, which in itself is another logistic regression node. And you basically keep repeating it. So you will have multiple of these nodes here in between. All of them produce an output that goes to the output node. And then finally, again, like logistic regression, it produces a single value that you can treat, for example, as a probability. Now, this whole network, you can add as many neurons as you want here, assuming that your features do not change. You can have multiple layers. So you can have actually this first layer of neurons that are feeding a second layer of neurons that may be feeding another layer of neurons here. And that's called deep learning. This is what deep learning is, that you go basically through multiple layers of internal hidden layers. In most cases, one is good enough. For engineering applications, one hidden layer is more than enough. Training neural networks is difficult because you go and you basically, what happens is that you have a set of inputs here and a single output. This is in your supervised learning problem. And you want to see how you can adjust all these weights the best you can, these W's that you have, in order to minimize the error between the predicted value and the true value. And since you're going through multiple nonlinear functions, that becomes tricky to find these W's. There are nowadays techniques for assigning weights relatively, let's say, through backpropagation algorithms and such like that. That's usually actually the main one, to assign the weights, but it's a computationally intensive problem. And then the other issue is that, how do you come up with these weights and to begin with, because I can choose all these weights to be the same as all of these and the same as all of these, and then these three neurons will essentially should be doing the same thing from that point onwards. I shouldn't choose all zeros, I shouldn't choose all ones. How do you choose weights? It's usually a random assignment at the beginning, and then you go and try to modify the weights using backpropagation algorithm and similar. Well, that's usually your main one. And you start to adjust these weights according to the basically errors differentials that you have at the output, and you go and try to adjust the weights of previous stages. It's computationally intensive at the end of the story, and it's always done numerically. And remember that we usually add our ones, right? So x naught is 1 here, and then we usually add a 1 here at the output to account for the biases and offsets as well. So what are the pros of neural networks? They're super powerful. They basically can essentially model everything. And remember, we said it's a logistic regression that we use at each node. It doesn't really have to be. There are other types of functions, activation functions you may be willing to use with their own nonlinearities, and they give you benefits in certain applications compared to the rest. Tons of degrees of freedom to play with here. They are widely used across the industry because they're so powerful, and there's a lot of open source implementations that you can go and pick. But the problem is that the training is complex and takes time, and you need powerful computers to do the work. Picking the correct topology is difficult. That is in terms of how many layers do you want to have, and then how many neurons per layer do you want to have. Usually, it's done with experience. There are some algorithms or some, let's say, rule of thumbs that you can use, but there's really no law. There's no definite way of choosing the number of hidden layers or the number of neurons in a hidden layer. A good starting point that should hopefully get you to answers more quickly is that you go and look at the size of the input layer. Let's say you have 10 features, 20 features, whatever, and the number of neurons in your first layer, hidden layer, should be about 2/3 of what you have at the input. So if you have 10 features, you're going to start with about, let's say, 6 or 7 neurons in your first hidden layer and see if it works. And usually that's probably good enough, a good starting point. And you normally don't go much above the number of your input layer or features, right? So let's say if you have 10 features, you probably don't want to have more than 15, 20 neurons for your first hidden layer. And then, adding a second hidden layer and a third hidden layer and so on and so forth, it makes the training a lot more challenging. So if you can do the job with one layer, if you have to add a couple of neurons, do it. It's better than adding another hidden layer. All that said, nowadays computation is relatively cheap unless you are using a microcontroller. Lots of variables that you have to set, all those weights, and therefore you need a lot of training data in order to figure out what those values are. And they're difficult to troubleshoot when you do not, when you see the algorithm is not working well. It's hard to say what you can fix. You can go and change the activation functions, you can go and change the number of neurons, all those things, but it's hard to say which one is going to get you a better performance at the end. And then the final model is incomprehensible in most cases. Why is this working the way it is usually hard to understand and figure out. So be aware of them, but I wouldn't use them, at least not at the very beginning of a machine learning problem or situation. Now, stepping away from logistic regression, we're going to talk about things that are relatively hard to understand, like neural networks. We're going to talk about something that is actually very easy to understand. And that is a decision tree. So what is a decision tree? This is basically a situation or an algorithm that tries to do the best classification based on one if condition, right? So it just looks at one of these features that you have in your data set, takes one of those features and tries to come up what is the best threshold here to split the data set into two. And then you basically create an if condition. If that feature is larger than a threshold, you go down this path. If it is smaller, you go down the other path. Very easy to understand. It's actually the way that most human brains work. Most humans are basically doing their classification. You try to do it in your brain, and then it's easy to follow that process. So for example, in here, let's say I want to separate make the largest separation between these data points. So I have three classes here. I have a class blue, a class red, and a class green. And I have only two features, x1 and x2. I want to separate these data set into three classes as best as I can. And then I look at this and I say, well, you know what? If I draw a line around here, I do the best separation I can. I can actually put the blue, let's say, samples on one side and then everything else on the other side. This gives me the best separation between these data. I know that I have 3 classes, but this is the best. So I go and look at the value for x1, for example, and say at x1, is x1 larger than 4.1 or not? If yes, you're on the green side. If not, you're on the red side. If you're on the green side, you have a good chance of being, let's say, belonging to the blue class. Okay? And then I keep repeating it. So this is the condition. So I have basically come up with a condition that tells me if the data point has, if x1 is larger than 4.1, there is a good chance that it belongs to class 3 here. If it is less than that, there is a good chance that it belongs to class 2, but it could also be class 1. So the next separation happens here. I look at it and I say, well, you know what? I draw another line here, or I branch out here. Based on the value for x2 this time, I make a decision whether this belongs to class 1 or class 2. If x2 is larger than that, I say it belongs to class 1 in this case. And if x1 is less than this threshold, it belongs to class 2. So right away, with 2 ifs and proper threshold values, I actually have done a very good job already in classifying these data points into 3 different classes. It's intuitive. I can go and do the same thing myself. I can keep going, right? So maybe this let's say classification is not good enough for me. I want to do, you know, I see there's a whole bunch of data points from class 2 in here. So maybe the next one is going to be this. I go and make a decision on this side of the curve based on the value of the other feature now. And now I can see that, you know, I've correctly identified all of these fellows that belong to class, let's say, 2. And then, you know, there are some class 2 items here that I identified as class 3, and there are some class 1, 2 here that I identified as class 1. I can keep going. I can keep branching out, right? And then improve this algorithm as much as I can. I can go and even create boundaries to single out a single data point and then correctly classify it. And the whole thing will be very transparent. You know, I can create that graph here, that tree that you see, it starts from the top and then you branch out. I can follow that. However, at some point, I should be able to see that, you know, I'm overdoing it. So for example, in here, dividing this whole region into 2 sections so that I correctly classify a single data point was probably an overfitting issue. Right? I'm trying to fit to that data point while, you know, if something happens to be in this region, there's a very good chance that it belongs to whatever class that was. It was, I think, class 3. Right? So I really do not have to take that strip out of that region because of one data point that, you know, could be there just because of noise. So what I like about decision trees, or what everybody likes about decision trees, is that they're easy to understand. It's easy to figure out what they're doing and how they're doing it. What is a bit tricky is to come up with those thresholds. And, you know, how do we pick this 4.1 that you see here at the top, and why did we start with x1 and not x2? So training them can be a little bit tricky, and it's not really as straightforward as using them once you have the tree. But I like them because they're easy to understand. And also, they often do a good job. However, you always run this risk of overfitting to your data. So a small change in your data can create a hugely different data set or tree for you. So for example, if we go and redo this problem, let's say we are using 70% of the data for training, you may get a division and distinction and thresholds here that are very, very different from the initial tree. So it's not super stable. You know, if you run it multiple times, you can get trees that look very, very different from each other. And you can get trees that branch out way too much. And you may want to go and say, you know, at some point you don't really need that level of precision. Your let's say, willing to sacrifice a little bit of that precision on your training data set in order to improve on the noise or error on the test data set that comes up later on. So what are pros? Easy to understand and visualize. They also, well, because you see what are the features that are basically creating the largest separations and distinctions between these data sets at the top of the tree, they can actually tell you which features are more important. So this is one of the ways that if you have, let's say, 5, 6, 7 features, you can create a tree and see which one of them show up early on and which one of them are basically down at the table that you want to, at the bottom of the tree. They can deal with numerical and categorical data, right? So it's an if, 0, 1, or a threshold. They can work with little data, right? So there's really not too many parameters to set, so it's a fairly flexible algorithm. The con is that if you're not careful, if you're not on top of it, if you're not monitoring what your system does, they can be over complex. You can go and divide that space into so many different regions that you get perfect 100% accuracy on your training data. But obviously that's too much, and it probably is not going to work well on new data. So you need to prune the tree. You need to get rid of some of the branches at the bottom of the tree so that you maintain a little bit of let's say, generalization capability. Generalization means that how your model works on new data, on data that it hasn't seen before. So we want the model to generalize well. And by pruning the tree, we may lose a little bit of accuracy or precision in terms of fitting to the training data, but usually it makes generalization a bit better, or the algorithm generalizes a bit better. And as we said before, small changes in your input data set, training set can cause or create vastly different trees. That's okay. What we can do here in this case is that we can create multiple trees in parallel, and we look at the output of the collection of them, right? So we basically, a new data set comes in because trees are super easy to implement. It's just a bunch of ifs. And if you go and look at some of the chips, for example, accelerometer chips that are, let's say, counting steps on their own, tree is what they use. A decision tree is what they use because it's just a number of ifs. Once you figure out the thresholds and you calculate the features, the algorithm is if this, that. If this is larger than this threshold, do that. If this is 0, then do this. Or go down this branch and so on and so forth. So they're super easy to implement. So therefore, creating multiple trees is not a huge deal. Once you have it, using them is not a huge deal. And you can basically look at what most of the trees in your forest are telling you in order to make a decision. And it could be that some features can dominate when you're building these trees, and in that case you can go and normalize your data. We'll talk about normalization of the data later on in K and N, but it's generally a good idea. If you're using a machine learning algorithm, just to be safe, you can normalize the features that your input and then process the normalized values. And we'll talk about a couple of ways of normalizing data soon. Now, another algorithm I want to talk about is Naïve Bayes. What I like about this algorithm is that it's, again, super easy to understand and visualize and figure out how the algorithm works. And it's very, very easy to implement. So the assumption here is that the data that you have collected comes from a process with some distribution function, right? So let's say some process with some distribution function has produced this data. So this is one class. A second class has a different distribution function. So they basically have data that looks like this. They are clumped together like this at a different corner of the space. And a third class will look like this, right? So in each class, so you assume each class has its own distribution function. Okay, so that doesn't sound too, basically too unreal. It should basically follow, it basically follows our typical intuition. Now, what we do is that we go and say, okay, give me your training data, and I know the classes that it came from. So I'm going to try to figure out, assuming a distribution function for that data for that class, I'm going to figure out that distribution parameters. Now, in this case, you assume that it's mostly a Gaussian distribution. So you go and say, these 300 data points belong to class 1 that comes from a Gaussian distribution. With the Gaussian distribution, all you need is to figure out what the mean of the data is and what the variance of the data is, or in a multidimensional space, what is the covariance of that data. And with that sample, with let's say those 300 data points, you can easily go and calculate the parameters for that function. For class 2, it's a different corner of the space. You go and calculate the mean and variance again, and you have a new distribution function. And then same thing for class 3 and so on and so forth. So each class is now represented, let's say, by a mean and variance, right? If you think about a 2D situation or 1D situation. If I give you a new data point, what you can do is that you can say, okay, I'm going to see how far it is from the mean of class 1 according to the variance of class 1, right? Or in other words, what is the probability that this new data point came from class 1, knowing the distribution for class 1. And I do the calculation for class 2 and class 3. The one with the highest probability wins, right? So it's that simple. It's that simple. And because it is so simple, I love it. We can see how it is doing its job. We can basically apply the algorithm quickly, and there's not much computation involved. Usually, the classifier here, the Naïve-based classifier, assumes independence between the predictors, between the features that you have at the input of your algorithm. It's often a good assumption, but there are many situations that it is not. So for that reason, it is called Naïve-based, because it naively assumes that these inputs are independent. The predictors are independent from each other. At the end of the story, I like it because it's computationally fast and simple. If you assume Gaussian, calculating the mean and variance is super easy. It works well in high dimensions, right? So in one dimension, it's just a mean and variance. In a multidimensional space, it's the same thing. You just get a matrix instead of a single number. Noisy data is not a big deal. If I have a Gaussian distribution, any value that is, let's say, a couple of standard deviations from the mean is a possibility. Your algorithm doesn't really care too much about it. It accepts it as a, let's say, low probability occasion. It doesn't try to fit to every noisy data point. That's what I mean here. However, in some situations, that assumption that the features are independent from each other may not be such a good assumption. So there are other algorithms that are similar in concept, but can take into account the dependence between the features. So all in all, here is a table for your reference. We haven't talked about KNN yet, k-nearest neighbor. It's going to be the topic of the next lecture. But decision trees, Naïve-based, and neural networks, or logistic regression you can add here, they all are arranged in terms of what we basically care about. I'm going to update this table and have a revised version in the slides that you will see. In most cases, what I care the most about is a good level of accuracy, not the best, but I want something that is computationally fast, and I want something that is easy to understand. Support vector machines and neural networks are excellent in terms of their accuracies, but they're hard to understand. If I can, I use something else. KNN is super easy to understand. Decision trees are easy to understand. Naïve-based is just, intuition. And any of those, I would probably try first, and then maybe try another one of those three to see what is the improved performance, if I gain anything. And if I'm unhappy with the performance I'm getting, maybe I go and try support vector machines or neural networks. We didn't talk about support vector machines in this course. I believe it is covered in some other courses that you will take in this department. So we just mentioned them without really talking about them here. So that's that. The next lecture we'll talk about instance-based learning methods that are really much easier learning, and then that will wrap up the discussion on statistical learning. So until then, stay safe, and I'll see you soon.